Hello, and welcome to Aggressive Physics. Today is day 82, and what I'd like to discuss today is standing waves. Now, we talked about interference of waves in our last class, and the interference of waves can be produced constructively or destructively. Now, it's important to note that when you have constructive interference, you have the maximum displacement of the wave particles, and if you have destructive interference, you have the minimum. For destructive interference, it could be a situation where there's no motion at all for some of the particles because a crest and a trough come together and cancel each other out. On the other hand, when you have constructive interference, two crests or two troughs come together and produce twice the amplitude in the vertical direction, positive or negative, depending upon whether or not they're crests or troughs. Now, we have a situation where the waves can possibly bounce back from a wall and produce a standing wave. And a standing wave is a wave that appears to be stationary but is in continuous motion. And the reason it appears to be stationary is because the wave going forward and backwards interferes with one another and produces a pattern that only has particles moving, if you have a transverse wave, vertically. Now, when you're going up and down, it seems like the motion of the wave is only up and down, and the wave isn't actually traveling to the left or right. However, the wave is actually still traveling. It just appears to be stationary. So a standing wave is just like the Doppler effect in the fact that the frequency in that case seemed to change but didn't. A standing wave appears to be stationary, but it really isn't. So a standing wave is produced in one or two ways. It can be produced when the wave reflects off of a boundary. And the reason that is the case is because when you send a wave and it hits a boundary, it often comes back, if the boundary is more dense, as the upside down equivalent, inverted. So if a crest hits a wall, a trough comes back. Well, when the crest hits the next crest, it's combining with the trough that's coming backwards. And what we have is a situation where the wave appears to just be going up and down at that single point. Well, what's really odd is there are spots on a standing wave that appear to not move at all. Now, we have terms for the spots that move and don't move. And if you remember from yesterday's lesson, when we had constructive interference with the speakers, we had antinodal lines. And when we had destructive interference with the speakers, we called them nodal lines. So antinodal spots on a standing wave are where you have maximum displacement, and nodal lines are where you have none. And here's how I remember the difference. Nodal lines, no motion. No nodal, so no motion. There's no motion at all. Antinodal, the way I think of this is anti-no motion. And if you have anti-no, you have yes, a little double negative for you. Now, if you remember nodal doesn't move, then it should be obvious that the antinodal lines do. Now, the standing waves can also be produced if you have two waves that are continuous and they're moving towards one another. So if you had two speakers producing the same note and they're traveling towards one another, you could actually produce a standing wave that way too. But remember, sound waves are longitudinal. So you have a situation where the vibrations are in the same direction as the motion of the wave. It's easier to visualize the transverse waves because it looks like a sinusoidal graph from math class. So you have the transverse waves that move up and down and the wave moves left and right. So the only motion with a standing wave is in the direction of the vibration of the particles. The wave itself is moving, but it doesn't appear to, and that's why you call it a standing wave. Now, that being said, if you have standing waves, some odd things can actually be produced. We could have a situation where you're asked to find the wavelength between two nodes or the wavelength between two antinodes. And what you have to remember that inside the standing wave is still wavelengths. You still have complete vibrations of the particles. You just can't see them moving traditionally left and right if it's a transverse wave. So what you'll have to remember is that the difference between two nodes is going to be half a wavelength. And the different distance between two antinodes is also going to be half a wavelength. So if you want to know the wavelength of a wave, you'll have to take the width of an antinode and double it. Or you could take the width between two nodes and double that as well. But just remember that the distance between two nodes on a standing wave or two antinodes on a standing wave is a half a wavelength. Now, there are a number of examples of standing waves in the real world. When we have instruments producing notes with a flute or a tin whistle or a recorder or something to that effect, you're producing a standing wave inside the instrument itself. If you pluck a guitar string or play a violin string or a cello or a viola, a stringed instrument, you're also producing a standing wave. Now, when you produce the standing wave with a stringed instrument, the bridge and the neck are going to be nodal spots, and the middle is going to be an antinode. So at its very basic level, you'll have one big antinode in the middle and two nodes at the end. And what will be true for all standing waves is that you'll always have an extra node because you'll have two tie downs at the end, and then you'll have one less antinode in the middle. So in that case, you could have two nodes, one at the neck and one at the bridge for the guitar, and then you have one big antinode at the center. You could actually produce what we call overtones, which are standing wave patterns that are 2, 3, or 4 antinodes with a single stringed instrument. You could even do that with a wind instrument as well. And all of these overtones are producing octaves higher in terms of their pitch. So we could have situations where you could produce higher notes by plucking harder on the string or playing harder with the bow, or if you're playing a flute or a tin whistle or something like that, if you blow harder into the instrument, you could actually produce a higher pitch by producing a higher order standing wave. We'll talk about that a little more later when we discuss instruments. Other examples of standing waves are you could actually produce a standing wave that could levitate water droplets. That would have the water, if they're very small and the sound wave is very strong, high amplitude, you could actually have the water droplets stay at each of the nodes, and the antinodes are producing enough energy to hold them up. Scientists early on, when they were working with sound, were actually able to levitate small tree frogs by using sound. And that is by placing the tree frog, because they're so small, at a point of a node, and then that would be held up by the antinode beneath it. So standing waves can actually be produced, can help produce levitation, although on a small scale. If we could harness the sound's energy and lift bigger things, we may be able to use that to move larger objects in the future. But right now we're stuck with very small objects. Another example of a Rubens tube is a Rubens tube, and that is where you have sound waves moving through a pipe that has holes in the top, almost like a fireplace, a gas fireplace, or maybe a gas grill. And as the sound waves change, it's going to produce different wave patterns. You can actually find videos of Rubens tubes online, but it's something that's dangerous because it deals with propane or natural gas, so it's not something I would suggest you do at home. I would leave it for the experts to do. But if you look at even things like Mythbusters, they have an episode on the Rubens tube, and that could be something that you can see an example of how the standing wave patterns change depending upon the notes that are being produced. You could figure out, knowing the wavelength and knowing how fast the wave travels in, let's say if it's a sound wave, how the temperature, how fast the sound is traveling in air, you can figure out the frequency of the note produced in a Rubens tube. You could do that with other instruments as well, with the fingering of the flute or tin whistle or something like that, and even figuring out how fast, let's say, sound waves travel on a stringed instrument if you know the note that you're producing, and you can measure how far apart the neck and the bridge are. So stringed instruments and wind instruments can be used to verify what the note is, or to calculate things like wave speed or even wavelength. So there are different things we can look at when we're dealing with instruments. But at the basic level, standing wave appears to be stationary. It's not really stationary, although the particles appear to just be vibrating up and down for transverse or left and right for a longitudinal wave. The wave is still traveling, and it's just the interference of the wave with itself, if it's a reflected wave, or with another wave of the same note if it is produced from two sources. So standing waves, just like the Doppler effect, it appears to be stationary, but it's not. Doppler effect appeared to have a frequency change, but it didn't. So this was our discussion of standing waves. And and tomorrow we'll look at the instruments. We'll start looking at instruments and how they're affected by standing wave patterns. This was Mr. Predwicki for Agrosive Physics, and I thank you. Now, as we discussed earlier, anytime a wave reflects off of a boundary, such as a wall, it's going to reflect inverted. And what will happen is that wave will interfere with the wave as it travels backwards. So you'll have a crest coming in and a trough coming out, and the result of that is what we call a standing wave. And it will produce a pattern that appears to be stationary, although it's not. So right here, we have what we call a standing wave. These areas have maximum motion. This area has no motion. So we have motion here and no motion here. Now we've come up with terms to represent motion or no motion. Where there's no motion and appears to be stationary, we call that a node. And I remember that as no motion, node. Now areas that move the most, we call antinodes. So it's anti-no motion. Now it's interesting to note, if we have a fixed end on both sides, such as maybe it's a guitar string or something like that, then these endpoints are nodes. And we have 1, 2, 3, 4 nodes in this example. And the antinodes would be 1, 2, 3. So 3 antinodes. And you'll always have one more node than antinode. Another thing to note is that the distance between two nodes is a half a wavelength. Consequently, the distance between two antinodes is also half a wavelength, but it's going to be a little easier to measure the areas that are nodes. So because of the reflection that's inverted, so it's 180 degrees out of phase, a crest comes back as a trough. If we send a continuous periodic wave, it will interfere with itself as it travels, as one wave travels forward and the reflected wave travels back. It's going to interfere, and we're going to produce a standing wave pattern such as we see here. What I'm going to do next is show you an example of that with the slinky. What I'm going to do here is create a standing wave with the slinky. And if I start at a slow frequency, this is actually a standing wave that's produced similar to a guitar. The two ends where I'm holding the ends of the slinky are similar to the neck and the bridge, and I produce a pattern like that. Now, many instruments can produce overtones as well, and that may be patterns like this. And you'll notice that there's spots where the wave appears to be moving, and there are spots that appear to be stationary. Now, the stationary spot, there's one directly in the center here. That would be called a node. And then we have two antinodes traveling in opposite directions as I'm moving this. Although my hand has to be moving in this case, so there is some motion, that's considered a node. The other hand that's stationary at the other end, that's also a node. So we'd have 3 nodes and 2 antinodes. Now, if I were to go even faster, we could produce even more nodes and antinodes. And in this case, I'm counting about 1, 2, 3, 4, 5 nodes and 4 antinodes. And if I don't keep it at the right frequency, what happens is we end up with a chaotic wave. So standing waves are only produced at certain frequencies. So I have to have this moving at the right rate in order to produce a standing wave. And it will only work at that particular rate. If I were to hold this tighter, that rate would change. I'd have to go a lot faster to produce the same standing wave. So the tension in the slinky is going to affect what frequency I would need to oscillate the spring in order to produce a standing wave. But what's important for right now is that the standing wave is produced, and we have an antinode that's moving and nodes that do not move. And at a slow frequency, we produce a single antinode and 2 nodes, and then we can produce more nodes and antinodes as we increase the frequency. and that's the standing wave.